Welcome to This Explainer. Today, we're embarking on a pretty wild journey. We are going to uncover the mind-bending connections across entirely different dimensions of human knowledge. We're exploring what I like to call the Map Multiverse. Okay, I want you to stop and really think about this for a second. What exactly is a map? Is it just that crumpled piece of paper stuffed in your glove compartment? Is it just an app on your phone? Or is it fundamentally something much deeper? Like a universal concept of structured logic that somehow bridges our physical reality, abstract math, and the digital universe we interact with every single day. So here's our roadmap for this explainer. 1. The art of cartography. 2. Reading the physical world. 3. Mapping in mathematics. 4. The map data structure. 5. Functional maps in code. And finally, 6. The universal thread. Let's dive right in. Starting off with Section 1. The art of cartography, from clay to satellites. We're going to ground ourselves in the physical world first, looking at how humans historically started charting their surroundings. The history of mapping our world is just this incredible timeline of human innovation. I mean, early humans were literally painting maps of places they'd seen on cave walls as far back as 6100 BC. Fast forward to the 6th century BC in Greece, and a guy named Anaximander is credited with creating the very first world map, though he assumed the Earth was shaped like a cylinder. By 1472 AD, we get the first printed paper map in Europe. But here's the really fascinating part, the leap to modern GPS. Did you know the US Department of Defense originally created GPS technology back in 1973 specifically to help submarines navigate? No way, right? It's wild that something designed for the literal bottom of the ocean is now the exact same tech guiding us to the nearest coffee shop. So all of this history falls under one specific discipline, cartography. It's the art and science of creating these maps. If we break down the literal Greek roots here, chartes means a sheet of paper or papyrus, and graphein means to write or draw. So a cartographer doesn't just sketch, they're blending geography, art, and cutting-edge tech to visually represent complex spatial relationships, basically so the rest of us can safely navigate our world. Now, when we map the Earth, we run into a fundamental physical challenge, which brings up the whole map versus globe dilemma. A flat map is incredibly useful, right? It's highly detailed, absolutely perfect for street routes or local topography. But think about it. When you try to flatten a 3D sphere onto a 2D surface, you're inevitably going to distort some shapes and sizes. That's exactly why places like Greenland look absolutely massive on a classroom wall map. On the flip side, a 3D globe gives you extremely accurate proportions and true distances, but it completely lacks the fine, close-up details you'd actually need to get around town. They're basically two completely different tools for two different jobs. But what happens when you need to map the actual, literal, physical shape and elevation of the world? Well, that brings us to Section 2, Reading the Physical World, Decoding Topography. A topographic map is essentially a 2D representation of 3D terrain, and there are 7 core features every topo map shares. But I want you to notice that very last point, marginal data. Anyone who actually knows how to read a map, they always look at the margins first. The margin tells you the map's date, its scale, its contour interval. Listen, if you skip the margin, you're literally just guessing. An old map might have outdated declination or missing roads. You absolutely have to read the margins so you don't end up lost on outdated terrain. And it's brilliant how these contour lines translate into actual physical landscapes. There are 5 major terrain features you're going to encounter out in the wild: hill, valley, ridge, saddle, and depression. Now, if you're trying to memorize these for, say, your next hiking trip, military navigators use a surprisingly hilarious mnemonic to remember them. Hidden Valley Ranch, salad dressing. Seriously. Hill, valley, ridge, saddle, depression. If you can remember your salad dressing, you can read the terrain. All right, sharp pivot here. We've mapped physical space. But what happens when we aren't mapping a mountain? What happens when we're mapping entirely abstract sets of information? Let's jump into Section 3, Mapping in Mathematics, Abstract Associations. I absolutely love this analogy from our source materials. In higher-level algebra, a function, which is also literally called a mapping, is compared to a machine in a factory. It takes raw materials, processes them, and outputs a unique finished product. In mathematical terms, a mapping is simply a strict rule that connects or relates elements from one set, which we call the domain, to unique elements in another set, called the codomain. The core concept here is completely identical to a physical map. A point here corresponds exactly to a reality over there. Now, in this abstract math world, these map connections take on some different behaviors. Take a look at injective versus surjective mappings.
An injective, or one-to-one map, means strictly different inputs will always map to different outputs. Think of it as a totally exclusive, unique pairing. A surjective, or onto map, approaches things from the destination side. It guarantees that every single possible output in the target area has at least one starting point or pre-image pointing to it. Basically, it ensures the entire target area is completely covered by the map.
Let's zoom in even further. Section 4, the map data structure, organizing the digital world. We're moving from abstract mathematical theories to the highly structured, super practical digital realm of computer science. So, in programming, a map, which is also frequently called a dictionary or hash map, is a fundamental data structure. It stores collections of data in key value pairs. The key is a unique identifier, and it maps directly to a specific value. It's honestly exactly like a coordinate on a physical map. If I give you the coordinate, or the key, user ID 101, the map takes you directly to the associated value, Sarah. And why do programmers absolutely love map data structures? It comes down to a concept called O of 1. That represents constant time average lookup speed. Because every unique key maps directly to a specific value, the computer doesn't have to sit there searching through a massive list one by one. It just instantly jumps right to the destination. That speed is exactly what makes maps the ultimate tool for fast, efficient software engineering. But in the digital world, a map isn't always just a storage container like a dictionary. Sometimes map is actually an active verb. And that brings us to Section 5, functional maps encode action over storage. Check out this JavaScript syntax, array.map callback. This method was introduced in ECMAScript 5, and it's a fundamental tool for array manipulation. Instead of writing those clunky, traditional for loops where you have to manually extract, change, and push data around, the map method gives you this elegant, highly readable one-line solution to transform your data. Here is the crucial point about how this mechanism actually executes under the hood. When you call map in code, it's doing three specific things. First, it iterates over your original array. Second, it applies a specific rule, your callback function, to every single element. And third, it outputs a brand new, beautifully transformed array. The real magic here is that it creates this new array without ever destroying or altering the original one. It's a total game changer and an incredibly powerful paradigm in functional programming. Wow, okay, we've covered a ton of ground today, from mountains to algorithms. Let's tie it all together in our final section, Section 6, the universal thread, a bridge between worlds. Let's look at the connective tissue binding all these disciplines together. Because really, whether it's a piece of folded paper pointing to a hidden valley, an abstract mathematical domain pointing to a codomain, or a JavaScript array transforming raw numbers into a new format, the core identity is entirely the same. A map is simply a bridge connecting one set of information to another. Its fundamental job across all of human knowledge is just to connect, to relate, and to help us navigate complexity. Which leaves us with this final thought. We started with cavemen literally painting on walls in 6100 BC, and today we are mapping massive data sets in constant time through digital microprocessors. Human exploration and our desire for structured logic, it's just endless. So I'll leave you with this question. From ancient clay to modern code, what will we map next? Thank you so much for joining me on this explainer. Keep exploring, and we'll see you next time.